Now, let us look at a little bit more complicated situation. That is, we still have a point charge where the electric field point in the radial direction is, and we want to calculate the potential difference between two points A. But now we want to calculate the energy difference, potential difference, not energy, between A and C. Is in this case, the line joining A and C is not along the radial direction. So, how could we do this? How could we do this calculation? We can use the similar concept as in the previous example when we discussed the calculation for the constant electric field, and we want to calculate the potential difference between A and C like this. In that case, you can see that we choose the path which can be divided into two parts. The first part is along the direction of E. Okay, the first part is along the direction of E. This is the first part. And the second part is perpendicular to E. And when we do the integration, you can see that the integration on the second part is 0. So we can perform, we have the same result when we calculate the electric potential between A and B. Right? We can use the same concept here. That is, we will choose the part. We can divide into two parts. From A to B. Here A and B, the line joining A and B is along the radial direction. And then the second part that join B and C. The line that join B and C is part of a circle. Part of a circle. Okay, it means that if you draw a line from Q to B and you draw a line from Q to C, okay, the radial distance from Q to B is equal to the radial distance from Q to C. So it means that if we draw a circle with the radius equal to the distance from Q to B, it will pass the point C. Okay, so we will choose this is the first part and this is the second part. Why we choose the path like this? This is a curved path. Okay, this is the straight line path. Why we choose the path like this? It is because we use the same concept as in this calculation. That is, in the first part, you can see that the electric field, if you write down the displacement vector dr like this, you can see that dr is parallel to E because dr point in the radial direction and E point in the radial direction also. So in this part, in the part A, we have that E is parallel to dr, and we have that E dot dr is equal to E dr. Okay. Now look at the second part. You can see that on this part, which is on the circular part, having Q as a center. So, at each point on this part, you must have that the part is always perpendicular to E. The dr is always perpendicular to E because because E point in the radial direction, but dr point in the tangential direction. Okay, so dr in the second part, you have that E is always perpendicular to dr, which means that if you calculate E dot dr is equal to 0. Okay. Now, when we want to calculate the potential difference, VB minus VC, we can have that VB minus VC minus VA. Okay, VC minus VA is equal to the integral from A to C of E dot dr, which is equal to the integral from A to B of this minus integral from A to B of E dot dr plus you have minus sign here, plus the integral from B to C E dot dr, right? But E dot dr in this part, which is the second part, is equal to 0. So you have that is equal to 0. So what you have to do is to calculate the integral from A to B like this, and you have the same result as in previous example. Okay. The potential difference is equal to KQ RB minus RA. But in this case, you can see that this is RB and this is RC. Okay, and from the definition of B of the point B, we say that B and C are part of a circle which have the same center and Q. So we must have that RB is equal to RC. So we can write the solution to be this is equal to the KQ of 1 over RC minus 1 over RA. Okay, because RB is equal to RC. This is very interesting. You can see that the potential difference between 2 points A and C depend only on the radial distance from the point charge to A and C. It's not depend on the direction. It means that it's not depend that A and C are along the radial direction or not. It depends on only the radial distance from the point charge to the point that we are interested. Okay, so we have in general this expression for the electric potential difference.